Imagine trying to write a traditional computer program to recognize a handwritten digit, say a number 3. You might start by writing rules. Look for a curve at the top, a loop in the middle, and another curve at the bottom. But the moment you look at the MNIST database, a collection of 70,000 handwritten digits compiled by NIST in 1998, you realize every single person writes them differently. A pixel that is pitch black in one person's 3 is completely blank in another's. Hard-coding thousands of nested if-else statements to cover every edge case is not just difficult, it is mathematically impossible. We need a system that does not follow rigid instructions, but instead learns its own rules from raw data. To build this learning system, we look to biology for inspiration, arriving at the artificial neuron, originally conceived as the perceptron by Frank Rosenblatt in 1957. The artificial neuron takes multiple numerical inputs, which we can label as x1, x2, and x3. Each input is multiplied by a specific weight, denoting its relative importance to this neuron. We sum these weighted inputs together and add a single number called a bias, which controls how easy it is for the neuron to fire. Finally, this total sum is passed through an activation function, like the sigmoid function or the rectified linear unit, abbreviated as ReLU, to introduce nonlinearity, allowing the neuron to model complex, nonlinear real-world relationships. Now we connect these individual units into a massive network. For our digit recognition task, our input layer consists of 784 individual neurons, one for each pixel in a 28 by 28 pixel image. This input layer feeds into one or more hidden layers where features are extracted. The first hidden layer might detect basic edges and lines, while the second hidden layer combines those edges into more complex shapes like loops or corners. Finally, the signal reaches the output layer, containing 10 distinct neurons representing the digits 0 through 9. The output neuron with the highest activation value represents the network's final guess. To calculate these activations efficiently across millions of connections, we abandon individual equations and turn to the language of linear algebra. We can represent all the weights between two layers as a giant grid of numbers called a weight matrix, and all the biases as a single bias vector. The activations of an entire layer can then be calculated in a single elegant step. We multiply the weight matrix by the input activation vector, add the bias vector, and apply our activation function to the resulting vector. This compact matrix formulation is why modern deep learning relies so heavily on graphics processing units, or GPUs, which are specialized hardware designed to perform millions of parallel matrix multiplications every second. When a newly initialized network first sees an image of a 3, its weights and biases are completely random, so its guess will be total garbage. To fix this, we need a mathematical way to measure exactly how wrong the network is. We define a loss function, such as mean squared error or categorical cross-entropy, which calculates the difference between the network's actual output vector and the target output vector. If we plot this loss against every single weight and bias in the network, we get a highly complex, multi-dimensional surface called the loss landscape. Our goal is to find the absolute lowest point in this mathematical mountain range, where the network's errors are minimized and its performance is maximized. To find that lowest point, we use an optimization algorithm called gradient descent. We calculate the gradient of the loss function, which is a vector pointing in the direction of the steepest ascent, and take a small step in the exact opposite direction. To calculate this gradient for millions of individual parameters, we use the foundational algorithm of deep learning, backpropagation, popularized by Geoffrey Hinton and his colleagues in 1986. Backpropagation leverages the chain rule of calculus to systematically compute the partial derivative of the loss with respect to every single weight and bias in the network, flowing backward from the output layer to the input layer, adjusting each parameter by a fraction dictated by the learning rate. This continuous cycle of forward propagation, loss evaluation, and backpropagation is repeated millions of times over thousands of training examples. Over time, the network slowly sculpts its own internal representations, adjusting its weights until it can recognize digits with over 99% accuracy. This basic mechanism of matrix multiplication, nonlinear activations, and gradient descent is the exact same engine that powers today's most advanced artificial intelligence, from autonomous driving systems to massive large language models containing hundreds of billions of parameters. By stacking simple mathematical blocks, we have engineered a system capable of discovering complex patterns in a chaotic world.